include alkenes. Alkenes. And just like alkenes, alkenes are also a part of the homologous series. And they are also hydrocarbons like alkenes, like how we saw that they are made up of carbon and hydrogen only, nothing else. Okay? Nothing else apart from carbon and hydrogen. However, now the difference with alkenes, somebody wants to be admitted or? Okay, it's okay. Am I presenting a screen? Yes, I'm presenting it. However, with alkenes, they are different from alkenes in that as alkenes have a single bond, now for them alkenes have a double bond, like how you see. Okay? And actually, this is their functional group. Okay? So these alkenes, they are unsaturated hydrocarbons that are consisting of a carbon double bond as their functional group. And actually, it is this carbon bond that distinguishes alkenes from alkanes and alkynes. So for you might see this as minor, but this one, it is so important. Why is it important? Because the two have totally different reactions. They two undergo different reactions. And the difference in their reactions is due to this double bond. Now, if you know the concept of hybridization, it is explained during introduction, and I explain it in details when I'm teaching the Form 5s. So in case you want, you can also attend with Form 5s, it is okay. But with this, the carbon is sp2 hybridized. And so it uses 3 of the hybrid orbitals or hybridized orbitals to form the 3 sigma bonds. That is one with carbon bond, and then another one with the hydrogen, and another one with another hydrogen. And so it leaves the pair, it leaves the empty orbitals, the p orbitals on each of the carbon. And so these empty orbitals can therefore overlap with each other to form what we call the pi bonds. Okay, the pi bonds. And so these pi bonds, they are the ones that result into the double bond that you see. Now the electrons that do occupy these pi bonds, we call them the pi electrons. And so because of the pi electrons present in alkenes, it makes them to be so reactive than alkanes towards electrophilic addition reactions, as we are going to see. Is that okay? Yes. Now, all of them, they conform to this general formula. All of them, where N is the number of carbon atoms. In that if you have one carbon atom, if you are made up of one carbon atom, then you cannot exist. There is no alkane, there is no alkene with one carbon atom. Okay? But the rest, they all start from 2. So if you have 2 carbon atoms, then you become C2, then H2N, which is H2 times 2, which is 4. And so this is ethane. And so on. So if you are drawing its structure, it is going to be C3, so the CH, oh god, C, then CH2, and then another H2. I told you the concept is one. The carbon atom, this carbon atom, cannot go beyond 4 bonds. And it cannot go below 4 bonds. It usually has 4. So this carbon atom, for instance, it has used 1, 2 to bond with another carbon. So it has a balance of 2. So the balance of 2 electrons, they are the ones that are used to bond with the 2 hydrogen atoms. Is that okay? So that's why this one is CH2, CH2. Then if you have 3, then you become C3, H 3 times 2, or 2 times 3, which is 6. So this is propene. We are going to see how they are named. Okay? And so its structure, it is C. Now, the easiest way, if you don't know how to write structures, first write the number of carbon atoms. Okay? But it is an alkene. Therefore, it has a double bond somewhere. And so then you start filling in the hydrogen atoms, where this one has used 2 to bond with carbon, so it can have 2 hydrogens, a maximum of 2 hydrogens. This one has used 1, 2, 3, so it can have a maximum of 1 hydrogen. And then this one has used just 1, so it can have a maximum of 3 hydrogens. So that is as simple as that. So about if carbon atoms are 7, so this one is going to be C7. Yeah, that's pretty good. H what? H14. And this one is heptene. If they are 9, and so on, and so on, and so on. So you can write them in your free time as an assignment. Is that okay? Now, how we name alkenes, if you remember there we used to name, there we named alkenes. You get the stem name, you add the word ane. Okay? Now with alkenes, this suffix ane is replaced with another suffix ene. Okay? And so for instance, if the stem name for this CH2 in alkenes, CH6, this we called this one ethane. Okay? Ethane. Now for alkenes, it is CH2, sorry, C2, H4. So we remove this ANE and then we add ENE. And so this one becomes eth, and then ENE. As simple as that. Is that okay? Can you name this? I know this one is easy. Can you name this? Can you name that? Drop your answers. Yes. So that one is octene. Octi is the parent name, and then in is the nomenclature. Now, how about if they are branched? So before that, so how about if they are branched? Maybe instead you have C, CH3, C, and then you have CH3 here. You name that, and then there is this one. A Let me make life hard. How do you name that? Yes, I hope you named. I hope I'm going to find your answers. So this one becomes, you consider the longest chain. So if you count this, it is 3 carbon atoms. If you count this, it is still 3. So it is whichever way, it is the same. Now, the carbon atom with a functional group is labeled carbon 1. So this is going to be 1, this is going to be 2, and this is going to be 3. Okay? And so therefore, this is just a methyl group that is attached on carbon number 3, number 2. So it becomes 2 with a hyphen, then methyl, methyl, okay, then 1, 2, 3. Then 3 is prop, but it is an alkene. So therefore you add ENE. So it becomes 2 methyl propene. I hope you wrote that. Good. Now few people are going to pass this. Few people are going to pass this. There is a 2 here, sorry for that. There is also a 3 here, sorry for that. So, do we have any? Yes, there is an H here. So the concept is 1. Hydrogens must have 4 bonds. So now when you are naming this, for instance, this is 1, 2, 3, 4, 5, 6. The concept is you consider the longest chain. Okay? And the longest chain here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now we have 2 longest chains. Okay? Now, your longest chain, let me even increase this to make you, to bring out my concept. This is a 2 and this is a CH3. Let me increase this to bring out my concept. Now, this is the longest chain compared to this one. Why longest? Because if you count from here to here, there are 7 carbon atoms. But when you count from here to here, there are 6 carbon atoms. However, now, your longest chain must contain the functional groups. Is that okay? Yes. And the functional groups in this case, it is this one and this. So there is no way how you're going to take this and you leave this with a functional group or this with a functional group. So as a result, we shall be forced to use this as our parent chain and then this as a group that is attached on our parent chain. So when you are naming this, therefore, it is going to be 1, 2, 3. And the 3 is attached on carbon. If we count from, it is the same thing. So it is, no. If you count from this side to be 1, 2, 3, 4. Carbon 4. But if we count from this side to be 1, 2, 3. So it is carbon 3. So we consider the lowest locant. And the lowest locant is 3. So it will be 3 hyphen. And this is 1, 2, 3. So that is a prop. But because it is a group, it is named as a group, then this is an alkyl group, and in this case, if you are to be specific, then it is a propyl group. So this is 3 propyl, okay? And then 1, 2, 3, 4, 5, 6. So 6, therefore it becomes hex. Now, because they are 2, then you need to specify it's 1 and 5. So it is hex 1, 5. 1, 5. Then diene. Now somebody must be asking himself or herself why I've written this one this side. diene. Now, this is how it is supposed to be, hex 15 diene. But there is another rule of IUPAC nomenclature. And this rule is the vowel stroke consonant rule. Now for those ones I've taught, they know better because I emphasized this. If I haven't taught you, I'm going to emphasize it. Now when you are naming, the vowel must be followed by a consonant, and a consonant must also be followed by a vowel. For example, here you can't say hex, okay? We don't consider this. So you can't say hex and again say die in. Now this one becomes wrong. Okay? A vowel must follow a consonant. So therefore, to rectify that, then this one becomes, you just write isomerism. Isomerism refers to existence of different structures but same molecular formula. You have the same molecular formula, but you have different arrangement of atoms to bring about different structures. So that one we call it isomerism. And alkenes also, like alkenes, so the alkenes, like alkenes, how we saw the other time, they show isomerism. I hope I'm still on. I hope I'm still on. In case I go off, you can always unmute and tell me. Okay? Yes. So alkenes also exhibit isomerism. And we shall, for those who are in Form 5, we shall study isomerism in details. And we see the different types. But for those who are in Form 6, we shall pass through it. Okay, so that we remind ourselves. So the first, they show chain isomerism. Now with chain isomerism, you have the same molecular formula, but you have different structures. Different chains. The difference is in the chain. Okay? The difference is in the chain. For example, you have C4H8. Okay? So it can be this, and this is N-butane. Okay? N is abbreviated, or is N is normal. So this is normal butane, okay? Not branched, just a straight chain of butane. However, this one is also butane. If I bring this one, if I get this and I bring it here, okay? And then I take this H, where? Here, okay? Then it becomes another alkene. And so this is N-butane and this is 2-methyl propene. Now this one, you can write it or you can't write it. It doesn't have any significance. Okay? So this is 2-methyl propene. And because of this, these ones, they are different. They have different properties. And they undergo different reactions. Is that okay? Yes. Then they also show position. Now with position, here you just vary the position of the functional group. The structure is the same, the molecular formula is the same, but just the position of the functional group, it is the one that changes. For example, you may have C, this is pentene, okay, and you have the pentene 1 or pent 1 in, where the double bond is on position number 1, is on carbon number 1. However, I can decide to shift this double bond from here and I put it here. Okay, and I bring this hydrogen here. So the position of the double bond has shifted, okay, from pent 1 in to pent 2 in. Is that okay? from here it is the same thing. So from here, it is the same thing. If I put this side, I shift it from here and I put it here. So which is what I've done. So paint 2 in. Is that okay? Yes. So that one is a different thing. These two are totally different. Or I can decide to put this double bond from here and I put it here. Okay? So it is still the same thing. This is paint 2 in. So it is the same thing. Okay? So those are the position isomerism that we have. But also on top of position isomerism, we can have ring isomerism, where you have an alkene and a cycloalkane having the same formula but totally different compounds. For example, you may have this is bute. Yes, this is butene. Why bute? Because of 4 carbon atoms. So this butene, it can be this, okay? And this is your butene. That's good. But surprisingly, it can also be this. Yes, in cyclo, this carbon atom bonded with this, and you form that cyclobutane. So these are different compounds and they undergo different reactions. Where this is an alkane, a cycloalkane, and this one is an alkene. Is that okay? So that is what basically isomerism is about. Then on top of ring isomerism, they can also undergo geometric isomerism. Now with geometric isomerism here, you have the same molecular formula, not just similar, but same molecular formula. But the way the atoms are arranged in space, the spatial arrangement of atoms in space is different. And so the rotation of these atoms across a double bond is restricted. Okay? You can't just rotate within a double bond. And so you form different compounds having different structures. Okay? Yet the compounds have the same molecular formula. For example, you may have but 2 in. Okay? And but 2 in, if you are to spread its structure, you can form such a structure. This one. Now I want you to see this. Where the identical groups are on the same plane. Okay? If this is the double bond, this is one plane of the double bond, and this is another plane of the double bond, this side. Okay? And so the identical groups, they are arranged on the same plane. Is that okay? And the hydrogens too, the same thing. So this arrangement, we call it the cis isomer. So this one is the cis isomer of but 2 in. Okay? Where the identical groups are on the same plane. However, there is another arrangement where the identical groups are on different planes, opposite planes. Okay? One is here, another one is the other side. Then one is here, another one is the other side. Okay? Then we call this one the trans isomer. And so when you are labeling, when you are naming, then you name this as cis but 2 in. Why 2? Because the double bond is on carbon number 2. This is carbon 1, this is carbon 2, and the double bond is just here. Then this one you name it as trans but 2 in. Why trans? Because the arrangement of the identical groups is on the opposite planes, okay? But also the carbon, so that the double bond is on carbon number 2. Is that okay? Yes. So basically, that's what isomerism is about. Now